And we are recording. Welcome to the evening of Python coding, where each month we bring you another Python tool or library and give you a short demo about it. Today, I'm very pleased to introduce you to Jim McCormack. I met him at AI Makerspace, where he was doing all sorts of very nice things with AI avatars. And now he's going to show us another library that deals with vision, but actually a set of libraries. But I rather him talk about it than me. Jim, the floor is yours.
Jacob, thank you so much. Let me share my screen and we'll get started. Just a quick check, you're seeing okay?
Not yet.
Let me double check that went.
Here we go.
Very good.
Now,
Thank you, Jacob.
yeah.
Still got me, Jacob?
Yeah. We're
Okay,
seeing your screen. Now we're seeing the GitHub. Go
okay,
ahead.
very good.
Tell us
Appreciate
what it's
that.
all about.
Okay, so let's get started. We'll keep it interactive. I'll try to work through this with you guys together interactive, and we'll have plenty of time for questions at the end as well. And what I thought we would do is we'd start out with my GitHub that's going to be able to, we'll put this in the show notes, and this is going to be the actual project we go over. So I've organized this into a repo you can clone either through the actual, clone button. You can just go ahead and do a git clone here and copy it down, or copy it as a zip and unpack it. And of course, we have a README file that goes with it. We're going to be talking about some computer vision today, and we're actually going to do some track and trace on ball movement or object detection and object tracing in a video. So you'll see that tonight. And we also have, I don't know if you guys use LM Notebook or Notebook LM from Google, but we have an explainer MP3 in the repo as well to revisit the code if you'd like. It walks you through the code. Just open the code and it'll give you a dynamic walkthrough of the code, much like I'm doing tonight. So you clone the repo, you run setup.py. It's going to create you a virtual environment separate from your existing projects. That's important. You'll have an isolated Python environment. You're going to install the dependencies, and you'll need to get an API key from the folks at Landing AI. That's one of the key libraries we're featuring tonight. And that key is free. It's not going to cost you anything. It is just a way that the package provider tracks usage so that people use their product responsibly. So don't let the key need intimidate you. So it'll automatically launch at the end of the install, or you can just type Python app.py to bring it up. So feel free to look at this later, walk through it. Gives you a pretty good explanation of how to run the code. So as I said, we're going to be looking at the Vision Agent library tonight. This Vision Agent library is from a company called Landing AI. And you may be familiar with Andrew Ng. Andrew Ng has a popular learning series that you might be attending. That's his this one here. It's called Deep Learning AI. That's his company that does this as well, but they also do this image library. So feel free, again, we'll put this in the show notes, but feel free to peruse the documentation behind the library as well as the PyPy behind it. Now, like many firms, they've got a lot of great resources to support their library. One I want to draw your attention to at the bottom of the PyPy is the Discord. Their Discord is actually quite good as well. So feel free to check out their Discord. So let me talk about the Landing AI documentation. We'll leave this link too. Just want to make sure you also know that the documentation behind the library is pretty extensive as well. So the APIs themselves, this is not meant to overwhelm you, but they have a rather robust set of image tools that you can use. Like for instance, this one here is maybe you're at work and you have applications where people upload images routinely. This is an end not suitable for work classification engine. You can check images to make sure people don't inadvertently upload things that are inappropriate to your Teams meetings or anything like that. For us and our purposes tonight, we're going to look at this Florence to SAM2 video tracking. And what that's going to let us do is track an element in a video across time. So for our use case, a golf ball, we're going to track this golf ball through a series of frames as somebody putts a golf ball. So this is another tool I just want to share briefly, and this is kind of their web UI to look at their tool set. So this is going to be, without even building anything, you can kind of play with their tools to see how they work and kind of test your use case. So for this one here, if I say, look, I want you to just isolate all the plants in the image, and I run it, this is kind of a nice visual. They have a pretty slick website here. This is going to do image segmentation. It's going to do a bounding box around the plants, and then it's going to do the detection for all the plants in this image. Now, it's my understanding when we run this, it actually spins up a container. So that's what the delay is about. It's usually pretty fast. So we see it come up with the bounding boxes, and we can see the number of plants in the image. So just to whet your appetite, another fun place to go without writing any code is to go out to va.landing.ai, va.landing.ai, and go ahead and play with their models. And when you get something you like, you can actually download the code, bring it over to ChatGPT, and continue to play with it. So it's kind of a way to jumpstart your dev as well. If you approve your use case, you can snatch the code out of here and then go ahead and use it. But let's get on with it. Let's get on with our use case for tonight. And let's start with the end in mind. What I thought I'd show you is, again, an application here where we're going to take an existing shot in video. And we're going to do this overlay to get the trajectory of the ball and a trace on the ball. So pretty straightforward, but it's a good use case to kind of assemble all the parts and pieces to do an image tracking exercise across time. So that's why I chose it. So I hope you're familiar. Sure, go ahead.
Run the second one again and show them with the mouse what it's showing, like what to look, because it's tiny. It's hard to see.
Yeah, maybe I can zoom that in. Good point, Jacob.
It's not to zoom in. It's the fact that they have to see what they're looking at, because it's like those yellow things are not very well.
Yeah, yes.
Show them.
Here we go. One more time on that. You still with me? I'm sorry. I've refreshed my screen, I think.
You'll have to refresh your screen again. They're not showing anything.
Sorry, I'll just run that. Go ahead and process the video. You guys will get a quick look at that processing in real time. But yeah, so what this is doing, right? You guys will just talk about it at 10,000 foot. So we have 5 seconds of video over here on the right and 30 frames a second. That's going to be 150 still images stitched together to make a video. So what we'll need to do to process is we'll need to break down that 150 images and to go through each image and find the ball. And then as we go, we're going to go ahead and track that ball across time. But what the software is doing right now that takes the most time is it's extracting those 150 individual frames, and then it will do tracking on it, and then it'll filter out some things that I'll talk about. It'll annotate the ball, and then it'll give it back like it has. So let's hope this, I can stop it to show you the video too. Let me play it through, and then I'll stop it so you see the ball trajectory in the orange behind it. So the novelty in this is really what we call, I'm doing some, I could just do a straight trace, and perhaps in hindsight that would have been better and more obvious, but I thought I would try something a little unique to kind of do like the hockey puck trace or something a little more sophisticated to fade the ball across time as it went frame to frame. So the ball is strongly colored at the front, and then it trails away in more transparent fashion. So it's not quite a straight line because I wanted to do something a little novel. But let's look at how we did that. Hopefully that'll make some sense, and we can come back to this and play it again. So let's go ahead and look at the code. So slow me down if I go too fast, but we're going to start right at the top. I'm going to work my way through this with you. We've got plenty of time tonight. The first thing we're going to do is import a set of libraries. The first one we're importing here is OS, and that's going to let us interact with the operating system and the environment. We're going to be able to save files. and interact with our operating system on our computer. And we're also going to load .env. This is a way for us to put our API key in a .env file, right? This is a way to get it out of our code, put it in this separate file, and then read it into memory as an environment variable. So .env and the .env file work together with OS to let us put our API key into memory and keep it out of this code here you see in front of you. The next thing we import is CV2, which is OpenCV, kind of the Swiss Army knife for image processing, and we're going to use that to annotate some images and do some things. You'll see that in action further down in the code. We also import NumPy. NumPy is, for the math end of things. So as we look at this ball on the video, that's going to be a location within the frame. So we'll need to build an array to kind of understand the XY coordinates, and we'll use NumPy to help us do that. And then we have Gradio. Gradio, it builds this UI. So Gradio is the tool that lets us set up the interface. And then the Vision Agent tools is T. That's going to be our Vision Agent tools. And I said, as I said earlier, that Florence de Sam 2 model, that's the model that's going to let us do that, the object detection. So we're going to do object detection and then map that across time. Then, of course, we're going to run some logging to give us some debugging if we need it. So the first thing we do is load our environment and our API. Like we said, with .env, we're going to load the Vision Agent API key, and we're going to put that into memory. Then we're going to check to make sure it got there. If for any reason that .env file that's in the same level of code as this golf tracker.py, if it can't find it or it reads it in there and it's an empty value, it's going to tell you, hey, I didn't find it. You can get your key over here at the landing AI. Just go ahead and sign up, cut and paste it into your .env, and then you'll be able to proceed. So it traps for that error where it can't find the key. Also, Gradio and Windows don't always get along. It could be kind of verbose and track a lot of errors with async IO. So we'll suppress anything but the critical just to keep the interface clean over on our console with Python. Just kind of some house cleaning there on the logging level. So the first definition we do is for a calculation of distance. So as we said, if we think about this project, we have this 150 frames of video. The ball will be making a movement in each of those frames usually, and we'll need to calculate a distance between, hey, where was the ball on frame 1 and where is the ball on frame 2, 3, 4, etc. As it moves, we're going to need to be able to calculate distance between 2 points and draw that line and do our trace. This particular NumPy is going to calculate a distance and then normalize it between 0 and 1. So don't get too bogged down on that, but we do need to calculate this Euclidean distance between 2 points, and we'll use NumPy to do that. So the next thing to do, our next function here, and we'll use this in the code, but we're defining these up above. So I'll talk a little about it here. Now remember, when we saw the image, we can see at the beginning when Tiger's about to putt, we can see a white image that's round that looks like a ball, but we can also see a white cup for the hole that might be misconstrued as a ball. So we have a potential for some problems, and we need to think ahead about that, right? It's definitely going to handle the ball, but what do we do to make sure it doesn't confuse the hole, the white circle of the hole, as a ball too? And when we think about that, we can say, look, one possible thing to do is to track movement. If it doesn't move, then it's not the ball we want to track, right? So we want to track moving objects only and not static objects. So this is going to let us do some filtering. So what we're going to do is set up 2 lists, one for the filtered tracks and one for the positions. And we're going to be able to pull in what we call a confidence threshold when we work with the model, and a movement threshold. So the model, when we say, look, detect balls, how certain were you that that white or that round element in the video, how sure are you that was a ball? So we can drive that confidence threshold very high and get fairly precise to try to cut down on false positives. And we can also track a movement threshold to say, in order to be a candidate, it has to move. So we don't want to look at things that don't move and misconstrue them as something we want to track. So this filter is about helping us set up this kind of a logic to go through all of the tracks, understand the frames in the tracks, and then filter them for first low confidence. If it's below 80%, if the model thinks it might be a ball, but it's not sure, if it's less than 80% sure, we're just going to skip it. We won't try to track it, and we'll depend on the model to filter out things that aren't really balls. And once we do have something that's a ball, we're going to create a bounding box, a rectangle around that ball, and then we're going to calculate the center, because as we plot across time, we're going to need to make that line kind of smooth. So we'll be plotting these center points for these bounding boxes in every frame as it finds the ball. We'll stitch those together. And like we said, these static objects like the cup, we're going to go ahead and check that the cup doesn't move. Each time we cycle a frame, we'll see that that cup is still in the same position, and we'll know it's safe to ignore. So that's what this filter is about. This filter is about these two things. One, is it confident it's a ball? If not, throw it out. Is it moving and it's a ball? Keep it. That's what this does. Now, once we have these functions set up, we can go to really the meat and potatoes of the app, right? The orchestration of how we work through the video. So this main processing function here at line 70, it starts with extracting those frames from the input video. We're going to track those frames in the Vision Agent tool. We're going to filter out any noise or non-moving detections. We're going to annotate those frames that have a ball with our fading trace line, and then we're going to save, restitch all those frames, and we're going to save our final annotated video. So we begin by processing the video with those inputs. That movement threshold, lower is more sensitive. So we have a very low value, so we're sensitive to movement. We want to focus on things that are moving, and then we have a 0.8 for confidence. We want to focus on things the model is confident are our candidate, our ball. And then we have this trace tail length, which is the tail behind the ball, set to 25, something you can change in the UI. So these flags are our status updates. So these are our flags here. We're going to be able to interactively update when we finish one of the steps involved in creating the video, just to give some UI feedback to the user. And again, the video initializes at none, and we'll build it up. Again, we're always doing the belt and suspenders check on the API key. So before we begin our try, we're going to start by saying, look, let's make sure not only that we have our API key, but also make sure that we have an uploaded video. So for instance, if somebody went without uploading a video to process and just pressed process, we would go ahead and trap that and say, hey, you forgot to upload your video. These two are hard-coded, but you could easily make this object label. You could easily make that part of the UI so that the application could do more than track a golf ball. You could upload, maybe a picture of an eagle's nest. I've definitely done this one where you could track if the eagle's in the nest. So you could upload a video of an eagle's nest, and then the object label would be eagle. And if it detected an eagle, for instance, it might email you and say, the eagle's in the nest, go have a look at the video camera. So that's static in our code, but you certainly could change this. And that's a good exercise for you guys to do maybe later, is go ahead and change this to something else and try a different video and try different sensitivities for the movement and for the confidence, and see if you can track the object you're interested in. So moving on, we've got our ball as our subject here, and we're going to show the trace every time. The first thing we're going to do is, again, we've checked to make sure you uploaded a video. We'll check to make sure you have your API key loaded as well. And then we'll go ahead and prepare our inputs for the video and our outputs for our new video. So let's get into the steps now. Here's where the magic happens. The first step is to go ahead and extract the frames. And we know that from our example, it's 5 seconds at 30 frames per second. It's going to be 150 frames. We're going to return those frames and the timestamps for each of those. And then we're going to be able to work our way through those. So now we have the frames. They're in the pipeline. We're ready to start our next step, step 2. The first thing we do, maybe I should point this out too, is the first step is extract the frames. We've got all 150. They're in the pipeline. They're ready. But let's go over to here and update the, let's go ahead and update the frames extracted checkbox to show that that's done. So the UI will get some feedback when this step's done, and then we'll continue on in the code with step 2. In step 2, we are going to use the Florence to Sam video tracking model to go ahead and find our subject, the ball. So that's where we're going to go ahead and do the actual vision agent tool call to go ahead and find the balls. So we'll go through that, and we'll do our object tracking, and once again update that flag on the front for status on the UI to say not only is the frame done now, but the object tracking is now done. Now we're going to look at all those frames where the AI model detected a ball, and then we're going to do that filter function we spoke of earlier. We're going to say, look, you've got X number of frames with the ball detected in the list. Let's look at the confidence threshold and the movement threshold and sort that out. We only want high confidence that there is a ball, and we only want those frames where the ball has shown movement frame to frame. So from the frame before to the present frame, did you see movement for the object that you identified as a ball? If you did, we're going to keep it. If it's static, we're going to get rid of it. So low confidence, no movement, those frames get filtered out, and we are going to work with the subset that is those frames with a moving ball. Now we're ready to annotate those frames. And this is, again, a little bit more verbose. Might have been easier just to do a straight trace, but I wanted to play with this a little bit on my own to figure out if I could do what we call an alpha calculation to, we're going to track the ball as it moves frame to frame, but we're going to age those balls in every frame, and we're going to change their transparency. So what this is a big loop to go through the frames and apply the logic to really shade those balls and then plot those points across time. So we focus on moving detections. For each moving ball in the frame, we compute that center point. We keep that coordinated list. As we talked of, it normalizes from 0 to 1, so we'll convert it back to pixels so we can get our pixel location in the frame. And we'll keep that list of the ball traces, and then we'll do our fading routine here to track our fade that you'll see when I run the demo. And then we'll update the UI once again to say, hey, we've done the frames, we've done the tracking, we've done the filtering, we just did the annotation, we're ready to do the save. So we'll move on to building that final list and then outputting and saving. So the final annotated video is all those frames where we've plotted that transparent or near transparent ball in them. We'll stitch all those together, and that builds that tail. And it across time, we continue to fade the ball as the movement happens in the video. So that's given us that trace effect here as we reassemble the output video. Now, one thing to draw your attention to is the frames per second output. That's settable. We entered this with a 30 frames per second video. The default on the output is 15 frames per second, just to save a little time as it recreates the video. And I'll show you that in the UI. Now, during the whole thing, we do catch errors. Again, we're hypersensitive that somehow we'll lose our API key. So that's the one thing that makes this go. So we continue to check for, hey, do we have the API key, or did we have an issue with the API key during this orchestration phase? If so, again, tell them where to get the API key if they don't have it, and print out the first 5 characters in case it's an expired key or one they didn't expect. So we're just trying to belt and suspenders our ongoing efforts to make sure we get a good API key. And then we update the final flag that the video has been done. And this last section is if we were to, do a second image or a second video, we just want to reset all our values to prepare for that second run. So this little function lets us reset all these static values in the flags so that we can run a second time. Now that's the main Python part to me. The second part here, this is really the UI, so I won't hammer this very hard. The UI itself, the Gradio UI you see here, is kind of a layout in columns. We have a column here, and then we have horizontals for different elements in there. And we have this accordion feature that's going to expose these sliders that are going to let us kind of change that frames per second output to usually 15 or 30. But you can trust the default, leave it right at 15, or you can change that. And that motion sensitivity, again, depending on your video and how much movement there is, you may crank it way down because it's pretty obvious that the ball's moving here. So I probably don't need a lot of sensitivity here, but you can play with that if you're having trouble with your tracking to kind of dial it in. What else do we have here? The tail length is just the amount of orange trail that you get there, so you can make that longer or shorter. And then the motion detection confidence, probably a really important one. How confident do you want the model to be when it says there's your subject is in the video, in the frame, the ball in our case? And we want it to be pretty strict. Otherwise, it might confuse the logo as a ball. It might confuse the cup as a ball. Could even confuse the club head as a ball. So we've got that cranked up pretty high to say, I want you to be very sure which one's a ball. So going back to the code, the rows involved, again, the columns are set up, the video input, the video preview, and the submit button, you saw that. And I walked you through a little bit of the accordion here and how we set up the accordion elements with these sliders that let us track the frame density on the video, the confidence threshold, and the trace for the tail behind the ball. Then the other element that's on the UI is, of course, those check boxes for the frame status. These five tracers over here are also tracked as well in Gradio. And we have our video input and output, so you can preview those. Again, the Gradio is pretty straightforward. Again, I'll highlight all the AI tools for both the Python code, in particular the Gradio. If you have any questions on Gradio, put that into an AI tool. It builds very good Gradio interfaces now. It's well-versed at that. Can give you a lot of help if you have trouble building the Gradio interface. The most important thing is our submit button here. So when we process submit, it's going to go ahead and initiate the whole UI to go ahead and work through the loop and give us and take in our inputs, and then go ahead and do the process and put out our outputs. And at the end here, we have our traditional Python conclusion here with just a little extra to make sure that if somebody does control break over on the console, that we exit gracefully. So let me pause there. That's a really quick walk of the video. Going back to it, if I refresh the screen, you've seen Tiger. Let's go ahead and do something a little more complicated. This is going to be a shot of somebody standing in the water, and the ball is going to jump up. So it's going to be a little bit harder. It may take a moment to process. So let me kick it off. And then let me also give you an opportunity to ask any questions you had about the code walk. Anything come to mind as we went through the code walk that needs clarification, or any observations or comments about the code? Anything you guys think you might do differently if you were doing it? You know, maybe a different tracking strategy or a different object detection?
Around the object detection, that what if you had something that was partially obscured at times? So an example, a person moving in a crowd or a vehicle moving on the road, where you don't always have full view of the object, but you may have a portion of it. Would that still fit with the confidence interval on object detection?
You might have to relax it a little bit so we could get maybe you could play with that to say, maybe you could have a gap for 4 or 5 frames, right? And then you could still trace between the frames after those dropouts, or you could relax the confidence and make sure you get those points. But good point. Mm-hmm. You'll have to play with that to dial it in.
Yeah, that's pretty neat.
So let's just real quick see how the model does trying to get a very high velocity and not a straight line. So I'll slow this down if we can't see it, but so it gets the orange in the air and it gets it roll. I don't know if you can see that. Let me try it again. Concentrate up here. You'll see the orange in the air. It does track it. It tracks it better when it's rolling on the green. And you might notice it also confuses the gentleman's hat. this seems like a ball to it. So might have to play with the confidence interval to try and get rid of the false positive on the hat. So it, that's the beauty of this. Sometimes you have to play with it and refine your approach and your model to see how you can do it. But the point on this stuff is it's pretty accessible and pretty easy to work with. It in the past, these kind of image calculations with OpenCV would have been more difficult to do. With the Florence to Sam model, kind of does the heavy lifting of the object detection for you.
Wilfred wants to ask a question. He raises his hand. Wilfred, did you press the raise hand button or something?
Yep, that was me. I was just gonna bring up regarding the ball, because it does get lost. The only thing I could see if that could potentially help with that is taking into account color, because obviously to you and I, we're gonna miss it because when it's in the air, it's and we're not looking at it frame by frame. If we're looking at it frame by frame, we'll probably be able to see it. It'll probably be kind of very, what do you call it? I guess it's going further up. It's the colors are matching, so you might want to have it to where, hey, looking like for shadows or seeing if they're in the same color range, and then figuring out how close in color range are they. Are they a point off? Because I mean, it's the difference between magenta or I don't remember the other one, but it looks like, yeah, an art guy's gonna notice the difference, but a normal person isn't going to. And so for this, you might want to put that in account where, like, hey, look for the color discrepancy between the hat and the ball. How close are they? And then I might add more to it, but then check again, like, hey, these are close to each other. Check again. It's attached to somebody. It's separate from somebody. If it's attached to somebody, it's likely not a ball.
Yep. It's a good idea too. I was just thinking too, like for this one, maybe this fade trace thing I'm doing isn't so good. Maybe that's good for putts, but just like when you watch golf, when they drive, which is super high velocity and they're showing it from behind, they do a straight line trace. They plot the whole thing. Like this would have been much better if I did a whole straight line arc where you could have seen the whole shot and left a distinct line for the whole ball trajectory and landing. So again, I would have to change the program. This fading trace for this shot is definitely not as strong as maybe a fixed line would be that showed the arc itself. Good thoughts. So again, the takeaway, right? So what is the takeaway? I guess
Gleb wants to ask a question.
Oh, sir, go ahead, Gleb.
Can I ask a question about measuring distance? So can you explain to me what units are you using in like distance? In what units?
So let's see if we can figure that out together, right? So in NumPy, right, what we're going to do is take the X and Y coordinates in terms of pixels. So,
I see.
So in terms of the pixel, but the pixel distance, we need to convert that to something a little bit more friendly for all the math we need to do. So the NumPy will use this function, line a align or line align norm. The norm is where it's going to convert that scale to between 0 and 1 to kind of make the math more manageable and doable. And then at the end, we'll reconvert it to pixel when we plot it. But we are using the XY pixel coordinates in the image when we start. Then we take it into this normalized mathematical array to do the vector and determine the 2 points and measure, the 2 points in the vector. I'm not sure that's super coherent on my part, but I hope it helps.
Thank you.
You can go on, Jim. I think the questions are done for now. There'll be more later.
Yeah, no problem. So again, just to hit the API key, if you go there and create your API, just to show you guys, like I've been using this since February, no costs. So the API is kind of some housekeeping to make sure they've got some tracking and tracing on who's doing what. If you upload bad images maybe or something, but the API is not a cost item for these guys. I'm sure there are things you could pay for if you do something more sophisticated, but the this agentic library has never cost me anything to kind of play with this stuff.
It's probably something for the future. It's just, in the future, this might be important for paying.
Absolutely. And I'll just give this deep learning AI with Andrew a plug too. Most of you may have seen this, but this is another really great free resource to learn about Python AI. And these libraries from Andrew and his company are really well done. And they're pretty sophisticated. So when we think about this, right, what could you use this kind of approach for? Now, a lot of people think of industrial applications where they're going to track part compliance, like maybe you're stamping out machine parts and you need to be able to look at them with computer vision to figure out if the part is conforming, or do you knock it off the line as a bad part? If you're doing filling soda bottles, right? You've seen all that. You can use industrial cameras at high speed to take photos and run the process and do quality control. But now, because it's so accessible, you could use it for things like queue time at your own restaurant. If you had a restaurant, maybe you have security cameras, you might look at some of that footage off that camera, and that would be good enough to say, what's the average wait time at my tables? How long does it take to get the check? Or how long is it to get the food on the table? And, you might be able to use more vision applications in your everyday life now because these libraries are much more accessible, and many of them are open source, so they're free now. So think about this. How could you guys experiment with vision now to do some use cases that you've been thinking about, whether they're sports tracking, maybe it's, you're using drone footage of traffic, your traffic, maybe it's traffic cams right in off your feeds in your neighborhood. You could do image processing to do flow control and understand congestion. All kinds of things come to mind. What do you guys think about it?
The applications are countless. Today, a camera costs nothing, and you can plug it in and do all sorts of things with it. You can detect people falling and stuff like that, if it matters, like for elderly and stuff like that. I'm not sure if this library or not, but there are libraries to do this. So if you have an old parent in the house that you're afraid that they'll fall, they can put cameras and see, and if something is detected, it will report to you. Even in Ivanov, he actually gave a talk about I think this, or he was dealing with this. He had a company with home cameras. So, but those AI tools are even newer than what was then. They only get improved. They're getting improved all the time. So
yeah, you can automatically annotate. If you're doing, maybe you're building an image model, right? You can now use some of these models to automatically annotate your images. So they'll help in the process of developing further models. They can count inventory. You can bring it in a supermarket, take a picture of a shot, like a shelf, like Pepsi and Frito-Lay. These companies want to be able to use security cameras and take pictures of their shelf space because they buy the shelf space, so they can pull frames off the security cameras and then automatically determine if they're getting the shelf space at the supermarkets that they're paying for as part of their contract. So many new use cases are emerging, and it's kind of a combination of the accessibility of the libraries and the fact that the models are good enough with AI now that they don't need a really sophisticated camera to get the images they can use.
Yeah. I wonder if this can be used, probably it can be used for like report stealing and stuff like that.
Absolutely. So shrinkage and, again, monitoring and time stamping. So you maybe, at a restaurant, you could tell who's more efficient, and in a positive spin, you could say, look, our best people are able to do things in this time motion. How do we interview them to learn that secret? How are they able to have this many table turns versus, what somebody else is doing, and maybe, supplement or augment your training programs to try and level everybody up.
Yeah, good use for self-protection. I mean, with the all the stalkerware around, it'd also be good for people who are trying to protect themselves. Like, hey, I'm looking for this person because And then now you're able to record, and it's aware, and it's always looking for this specific person. That way, if they're going against their what do you call it, the restraining order,
Sure.
you can now like, hey, I recorded it. They were here at this time, as I've been telling you. They're always coming here at this time, or around in this range. Here's the video, showcases them right there.
Yeah, and at schools you could track weapons, all those things, right? So you have these video cams, and they could alert when they see a weapon. They could notify resource officers at school. All those things come to mind. It's it's cuts both ways, right? It is surveillance, but it does it will proliferate because the technology is becoming so accessible. But hopefully we have some good ethics about how we apply it. You don't want to stalk people with this, right? You'd be like, oh, this person's here now and I can go find them there, right? But yet if somebody had a weapon at a school, you'd certainly want to know about that as soon as you were able to see that. Not when somebody put eyes on them, but when a camera put eyes on them. Maybe in the parking lot, right? Versus in the school.
It'd be at least nice to know when, like, hey, we saw some random person around the building just drop something randomly, and then couldn't find out it was a USB because they're hoping that somebody will pick it up and pop it in their stuff, or maybe you're on the lookout for somewhere, maybe you're just sitting in security and you get a silent alarm that at least lets you know, like, okay, I'm not going to do anything right now, but I'll be looking in this general direction because it might be something, it might not be something, but at the very least, what you might have just looked at as like, yeah, nothing to worry about. You might say, let me put some extra eyes on that just to be aware.
Right.
Well, any more questions?
It's an interesting thought in terms of coupling this with drones, where the video feed from a drone potentially could be used for tracking something on the ground as well.
Yeah, crop, agriculture, definitely military, right? But definitely crop too. Like, or, animal movement, migrations in Africa, the antelopes come to mind, all that wildlife, or tracking elephants or scarce game, trying to, intervene if there might be poaching. You could definitely, elephants might again eat crops if they, in certain countries, the elephants will, in India, it comes to mind, right? If the elephants roam off the range, they will eat crops, and then the farmers will get in a confrontation with the elephant, and the elephant will hurt them more often than not. They don't usually hurt the elephant, but the elephant can rampage and cause problems. So you definitely want to use these kind of tools to track certain wild animals to understand where they are and go intervene before they get to where humans are and turn them back, etc. That's a great use case.
Okay, more questions? Questions going once? Questions going twice? Questions going 3 times? Okay, no more questions. So I would like us all to thank Jim for his very nice presentation. Don't go away. We're not done yet. We're just finishing this part of the meetup, which is the demo. I'm going to stop the recording in a second. And
thanks for being such a great audience too. I appreciate everybody being patient with my talk tonight. Thank you.
Jim, what patient. You've done a great service to us all. Thank you very much. I'm stopping the recording here. Don't go away. We're not done yet.